Hello, Dietrich, can you hear me? I can't hear you.
So Simon, do you hear me?
Yes, now I hear. Yes, now I hear.
Far away from me also.
Do you have a recorded talk or will it be online?
Oh, it's a recorded talk.
Okay. So you can enjoy and admire yourself.
I don't know. I don't know what came into this thing. So it can be anything, you know.
Well, you will also
close my eyes and ears.
Now Prasad is saying something that I can't hear.
So now I see you, Simon.
Yes, I just my hair is not very well, but what can I do? Too late. But Prasad, I can't hear him.
I can also not hear.
He left us alone.
Yeah. I don't know. I was a bit confused with time also because I didn't think it was Indian time on the schedule.
Yes, it's pretty early. The morning wake up was this morning very early.
At least. Have you followed the rest other sessions?
I was most of the time I was following. Yes.
Because I became a bit nervous, you know, that one doesn't know what is going on.
Yes. But I can congratulate yet the picture that I see from you. It's very nice. You look very good.
Ah, thank you. Okay.
It's high quality. Now I have great expectations regarding your recording.
Oh, this I don't. No, I really haven't listened to it. I couldn't open. They sent me a file, but I wasn't able to open it here. So I have no idea what will come out of it. It's not so easy, in fact, I think, to talk into a screen without audience.
Yes, exactly. Did they record your talk or did you do it yourself?
No, I haven't done it. I was just talking into the screen.
So on your own.
What the result was.
Now there seems some action. But I have a people call. It's my own voice.
Yeah.
It's really bad.
But technology
I guess they could more or less put the recording on.
Hello? Hello, audible, sir? Hello?
It's from the moon.
Hello?
Hello?
Sir, can you see me?
I can see Dietrich and myself.
Okay. Huh? You can hear me, no?
Yes, I can hear you. I can hear you now.
You can see me also. Okay.
Yes.
Okay, problem is sorted.
Okay.
Since the morning, some problems were queued up. One after another keep coming and we keep sorting it out. And now we'll continue. Okay. Good afternoon from here, and maybe Sima must be having good morning now.
Yes. Very.
Okay, you also, all right. Okay.
I have my coffee cup here.
Oh, what is it? Okay, I'll hand it over to Raksha to take care of the session,
Okay.
and she will invite you formally.
Good afternoon, everyone. Welcome back to the afternoon session of IWMS. So in this session, we have with us Professor Dietrich von Rosen from Swedish University of Agricultural Sciences, Sweden. He is honorary doctor from Tartu University, Estonia, and also guest professor from Central University of Finance and Economics, Beijing, China. He is also editor-in-chief, Journal of Multivariate Analysis, associate editor of Discussions Mathematics, Probability and Statistics, Journal of Multivariate Analysis, etc. And his area of interest are multivariate analysis, probability and statistics, regression analysis, and the list goes on. So we are very happy to have you here, sir. His title of the topic is Matrix Decompositions in Linear or Bilinear Methods. So I request Professor Simo Puntanen from Tampere University, Finland, to chair this session. Over to you, sir.
Thank you. I have a great pleasure to sit in my chair and chair this forthcoming session. I know I cannot interrupt Dietrich for 1 hour, 30 minutes, something like that. That is quite a long time when I'm not interrupting you. But anyway, I guess that we have very interesting time in the front of us, and let's put the wheels rolling. Can you put the recording on? Dietrich will speak.
Recording is in progress, sir.
This looks like live.
Yeah, ladies and gentlemen, it's a great honor, pleasure to give you this unusual talk, unusual in the sense that it's pretty long and it's virtual. Before starting, I would of course like to thank the organizer for inviting me, and it's a pity one cannot visit you on place, but I'm looking forward to do it some other time, maybe next year. So, title of the talk is On Decomposition of Linear Spaces Connected to Linear and Bilinear Models. And here's a short outline. So I'm going to talk most his first part about the models.
And that's mistake.
Sorry professors, we have some technical issue here. We will sort it out soon.
It's a great honor to give you this unusual talk, unusual in the sense that it's pretty long and it's before starting, I would of course like to thank the organizer for inviting me. Pity one cannot visit you on place, but I'm looking forward to do it some other time. So, title of the talk is on the composition of linear spaces connected to linear and nonlinear. And here's a short outline on the first part about the models, linear models, multivariate linear models, and the second part presents some tools and what kind of results one can find in various, say, easy ways. And then in the last part, I will talk about how I can use this knowledge to produce some results for models which are not really connected to linear or multivariate linear models. But still, we can use the knowledge from, say, models. If you think about the most common univariate linear models, then we have the analysis of variance model, Manova regression model, and the analysis of covariance model. And this is of course a classroom presentation now. If you have two treatment groups, you want to compare them. In this case, I have the melatonin. I will return to it. It's a hormone, sleeping hormone, but this is not essential. We want to compare two groups. And this we can do in the following model here, that we have observations Yij or random variables correspond to observations. We have a mean, and if there are two groups, I equals 1 goes from 1 to 2. So we have mu1 and mu2, and we want to see if mu1 equals mu2. We have an error term. In this case, all the errors are independently distributed and have an unknown variance sigma square. So the unknown parameters are mu(i) and sigma square. And this model can be written in a general linear model. So we have a vector yi, I make the transpose because I usually talk about column vectors. We have an unknown parameters in beta, we have a design matrix C, and we have an error vector here. An error vector is written this way. It's an n dimension if we have n independent observations. If we go to regression, they can be a bit more complicated. Here we things we have taken observation of the sleeping hormones over the day and night cycle. And so we have individuals here and time 12, 16, 20, and so on. And this model can also be written in as a general linear model. Y transpose equal beta transpose C plus in E transpose. And the only difference is with the ANOVA case is the construction of the C matrix. And we can extend this a bit to combine this with the analysis of variance with the covariance model. And we have some analysis of variance model. Previously we called it mu I, mu J, but in principle it's nothing here that we model two curves. So in this can be two treatment groups, and we can look at the response over the day and night cycle. And once again, by choosing or creating the C appropriately, then we have a general linear model. So what is going on here a bit? If we would do a likelihood approach, we have the likelihood, then we would get the normal equations that are given here. And then the normal equation, this is when we say difference with respect to the mean and beta. If we solve this equation here, we get this well-known least square solution, which is maximum likelihood also in this case. And what I would stress a bit here today is that this part here is a projection. So it can be written that beta hat prime, the estimator, times C equals Y prime times the projection C prime. And then we have the residual, and residuals are usually defined as the difference between the observations, Y observation, and the estimated mean. And the difference here, yes, the straightforward calculations gives that we have at the end here Y prime equals identity minus PC and projection on the column space of C transpose. And this is identity minus this, you know, this is also projection, and it's a projection on orthogonal complement on the column space of C transpose. If we square the residuals, we find the estimator of sigma square, and if we divide this here by n, we get the maximum likelihood estimator. Sometimes we want to have an unbiased estimator, then we divide it by n minus the rank of C. So the ingredients we had here were the observed model, we had the mean estimator, we had the residuals, we squared the residuals to get the estimate of sigma square, and this can be, everything can be summarized in this figure. So here we have the mean space, and then we should project our observation on the mean space on the column space of C transpose, and in order to get the residuals, we should project observation on the column space orthogonal complement to the column space of C prime, and then square. Then we get the estimate, but all model validation and things goes from this part here. If we generalize this a little bit more generalized, we say we can put some restrictions on beta also, and these are like they introduced as a linear equation. So if we have a linear equation, we solve this, and then we get the solution here. This GO is any matrix which is generates a basis in the column space of G. So this is a solution, and what we're doing then, we're plugging in this solution in the model here, and then we are back into linear model. I see that here's a mistake, that it should be not the transpose here, or we should switch here. So the end will be that we're plugging in this, we will still be in see this usual linear model situation, and then we can form the projection in this way, as here. So the projection is summarized with the projection on the column space of C prime GO. And in particular, one can have sometimes if something is subspace to column space, but I will not go into that into detail really. Okay, so and then what we can see here that we have a projection here. We need its orthogonal complement. The orthogonal complement can in fact be split into two parts. One is given here, and the other is usually what we had before. And this part here, when split, is an intersection between and the orthogonal complement to this space intersected with the column space of C transpose. And here's the decomposition. This square box just indicates that it's a sum of orthogonal spaces. And the picture, which is nice to have in mind, is that we have a mean space under restrictions, so it's a bit smaller now, and then we have a bigger residual space. And inference is in principle about what happens to this space here. If it's small, then there's no effect of the restrictions. If it's large, the restrictions have an effect. And this can be tested, for example. Another generalization is if we don't have IID errors. Instead, we suppose that we have a post-indefinite covariance matrix, there's some dependence, and then we get normal equations of this form here. And the normal equation, this is once again a linear equation in beta. We can solve it. The solution is given here. And then we see that the projection here, it's we have a V inside, and it means that this is a projection on a space with an inner product. And the inner product is defined by V. And then it turns out that we should have V inverse inside. And this is, of course, on the assumption that this is positively definite. So the estimator is given here. And then we define residuals in the same way as a difference between the observations and the mean. We come up with projection of this type, and then we form the estimator sigma by multiplying together these vectors. But now observe, we should multiply it with the V inverse because we are working on a space where we should work with an inner product. So all this comes together, and then we find our estimator sigma square. So once again, we have all the model, we have the mean estimate, the residual, we have the variance estimate, and we have the picture here. It's just that now we indicated how this projection should be, that it should take into account that we have an inner product. But otherwise, everything is the same. If we go to a multivariate situation now, that means that instead of having one hormone here, the melatonin, and we have 4 different hormones. And we still can maybe have 2 groups. So we have a response variable from which consists of melatonin, cortisol, TSH, and prolactin. And this can be formulated in a multivariate model or a Manova model. And if you compare this with the univariate model here, the difference is not so big. It's just that Y is now P dimension, it has a P by N. It's a size, previously it was P was equal to 1. This was not indicated here. But we have exactly the same C matrix, design matrix, because we have exactly the same design. It's just that our response is not one-dimensional anymore. And then we have an error. Instead of 1 by N, we have a P by N. We still have, and then we think that each column, there's a dependency. This dependency is described with sigma. And then we have N independent columns, as before. Here we have sigma square, we just call it sigma, but this is a matrix. So we have variances here, and we have also covariances, which doesn't exist here. However, if we do maximum likelihood estimation, we will get the normal equations, and they look in principle the same as in the univariate. So here we have the normal equations. Yes, we have a B here, which is a matrix. Here it was a vector, and then we solve it, and we solve it with the help of projections, or it turns out to be projection. We have the residual here. We have the residual here. Here's also we have the observations minus the estimated model, and then we get the residual. And then if we square the residual, we get the estimate of dispersion. So this is complete analog. And we can look at the pictures here a bit, that we see that we have, here was the column space of C transpose, here it was its orthogonal complement, we had the projection on the mean space, we had a projection on residual space, and we have exactly the same here. It's just that we have quantities which are p-dimensional. We could also formulate things here a bit different. If we take the vectorized, then we get the huge linear model, and then we get the design matrix of this form, and then we have, in fact, some kind, if we take the column space of this and we return to it, it will be a tensor product, and this is that part here corresponds to this part here, and the identity means that we have the whole space. There's no restrictions here. It's up to P. Size P is that space. Okay, if we go to the growth curve model, the situation becomes a little bit different. And this is not the linear model in size, it's bilinear model, because we can have some matrices before and after the mean. So we have the same observations as in the Manova, but we have a design, say, over repeated measurements. So which is A, and this is P by K, this is maybe K by or Q, and Q by K, and this is K then. The C matrix is exactly the same design matrix as before. And we could have repeated measurements on individuals. Here's the melatonin, but now we have the same individual is observed over the day and night cycle. Previously in the regression model, we had different individuals at different time points. But now we follow the same individual over time, and we have two treatment groups, and we are interested, is there a difference between these groups in some way? So with the A matrix, we model the structure, how it looks over, like in the regression, that we have this day and night cycle, and C models the design, in this case that we have two growth curves. And before giving a picture, I can say a bit how to estimate things. And it's also, if we suppose first a sigma is known, we have the model here, sigma is known. We can go to linear model theory if you want, because sigma is known, there's nothing mysterious here. But we come up, whatever we do, because it's normal equation, that the normal equation are of this form. And the solution is more interesting because this is a linear equation in B. So there is, and it's homogeneous. So there is, no, it's consistent. Sorry, it's consistent. But the solution exists, and it's given here. And then we once again can see that we have projections. So the estimator of ABC is given by two projections. One is the same as before, that we project on the column space of C transpose, and the second is that we project on the column space of A, but now we have to take into account that we have an unknown covariance matrix sigma, which not unknown, sorry. We have a sigma which acts as an inner product, or it has an impact on the inner product. If you look at the pictures now, we have the Manova picture here, the whole space, but with the growth curve, since we had the model on A, we reduce this here, so we have just say the corner on which we project. And this is what we did before. We projected on this space, and then we immediately see that the residuals, they connect are either two spaces if we merge them, but we can also decompose them in three spaces. So that space, and that space, and each party has its own interpretation. if you look here at the growth curve model, and I claim that I want to say that the estimator of this here with an unknown sigma is given here, and I will later show you how one can do it or technically. But I will, as you can see now, we have projections, but instead of sigma we have S. So instead of so this is the projection here. And in the dispersion matrix, we have this S here, and then we have also another space or another projections which are defined here. And this can be technically shown, but I will just show you a picture how this can occur. And here's a picture. So there are in principle two steps then in the maximum likelihood approach. The first is to estimate the inner product. And this one is due from this part of the space, and that will generate an S. So what we are going to do is to replace sigma by S. And once we have done it, then everything is about projecting on the mean space. And that will give our estimators here. So the first, replace sigma by S or SON, doesn't matter. And then in the second step, we do the projections. And what you can see also, this S consists of these two. So we square these two residuals, this is indicated here, and then we come up to this expression, as we had in the Manova. For the growth curve, we can see also, if you put the bilinear restrictions of this type here, it means in some way that we cut out a part from this square. Take away it, and then we see that we are outside the growth curve class, because you see it's about some kind of stair structure, and it means this belongs then to a class of model which we call extended growth curve models or extended bilinear regression models here, or sum of profiles models. There are many names. So there are two versions of it. One is when observations are here, and then there are sum of profiles and the error. But what is new here, that we need to put some kind of restriction on the design matrices. So this is an intersection, is a nestedness, which we need. But we can also put the nestedness on the A matrices. And they are in some way equivalent. Also there can be advantage to use either model 1 or model 2. And because this nestedness, we can come back to this expression that we can see that we have a stair structure. This is indicated, or it follows due to this nestedness condition. If we wouldn't have that, we wouldn't have a stair structure. And this condition is needed in order to find explicit estimators. Here's just some data. I will not say much. It's the classical Potthoff-Roy data. But the idea with the extended growth curve model is that in the growth curve model, we assume if we have a linear structure here, we suppose that both, say, treatment groups follow a similar type of linear structure. Not exactly the same, but if it's linear, it should be linear for other. But if you have a quadratic response, for example, for one of the treatment groups, then we can use the extended growth curve model. And this is here, for example, for the boys in the Potthoff-Roy data set. There's some indication that there is some kind of a second order growth instead of linear growth here. And here's once again the stair structure clearly indicated for nested. Here we have 3 profiles. Then it looks like this. And if we estimate, I will not give you the technical details so much, but it works like this, that first we have an estimated from here into of the inner product of sigma. Then we project on this space here to find some estimators function of the other parameters. And after projections, we come up in the model class of this here. We update our inner product from the first part by this part. And then we do projection on this part here. And at the end, we come to the growth curve model, and then we know how to do. We can also construct residuals here in different. So for this stair structure here, we have 4 very natural residuals compared to the growth curve where we have 3 residuals. here we have split them into two. We could have split this also in many parts, and each part in some way has some information about data. So this was part one. Now the first part was a very quick introduction to models which I want to handle. Now I come to a bit more technical part, but it's easy to talk about projections and column spaces and whatever, but it's also so in more complicated models, or in principle all models, one needs in statistics, one needs concepts of like the intersection and sum of subspaces. And now I will show you some technique about how to work with this, say, to derive quick expressions for the projections. So, and you will see that I will go into lattice theory. I think this is extremely useful tool. It's not so exploited among statisticians, I would say. Also, it's well known for a long time. But yeah, let's start to see what. So this is about, we started from a mathematical point, and this is about partially ordered sets. And partial order sets is given here with 1, 2, 3 conditions. So we have ABC belonging to a set A. So if A is smaller or equal to itself, or if A less or equal to B and B less equal to A, means this should mean that A equals to B. And if A less or equal to B and B less equal to C, then it's possible to say that A is less or equal to C. And these three relations define a partial ordered set. More important is that we want to find a least upper bound of a set. It means that for the subset in to A, call it H, every element in H should be bounded or be smaller than A. And of course we haven't defined really what these inclusions means, but we can just say smaller. And the same, we have also a greatest lower bound. This is upper bound and lower bound. And a lattice is a partial ordered set, and to the lattice, both the smallest and the greatest lowest bound and the smaller or the least upper bound, the smallest upper bound, if they belong to the lattice or to the set, it's a lattice. And we should see that for any lattice we have these conditions which should be fulfilled. And if we now leave this algebraic part and just look at vector spaces, or finite dimensional vector spaces even, then we see immediately that these conditions are fulfilled when we see this as a subset or subspace. A is a subspace to itself, A is a subspace to B, and B is a subspace to A, then A equals B, and the same, we have A is a subspace to B, and B is a subspace to C, then A, or it should not be smaller here, it should be a subspace to C also. But more important is that this smallest number, the smallest number is the intersection between A and B. And intersection means that any element here in this intersection should belong both to A and B. And then we have the supremum, and this is the greatest lower bound. This is a union or the sum of n spaces. You can call it the sum A plus B. This is maybe more natural vocabulary. And it means that for all elements where x equals to A and y equal to B, all these combinations, it gives you a linear space. And this is called A plus B. So then I will show you some, say, relations, laws, and I just translated from lattice theory. So if we intersect something with itself, we have A union A, and we have some commutativity here. For A intersected with B equals B intersected with A, and these are pretty trivial in some all these things here. And this is true for any lattice, what we can see. And more important, which are directly connected always to our linear models, is about distributivity. We usually want to have, say, if we talk about spaces, we want to have be able to add it. So, for example, that the A intersected with B plus the A intersected with C, it would be very nice if A is intersected by B plus C. But it's not true. We can only say that this is a subspace. So usually we want to have this kind of relation in statistics. For example, analysis of variance and other, where we decompose something, we would be able to decompose it in subspaces which are interpretable. And these spaces are usually interpretable, but this is it can be more complicated. And then there's always a dual statement here to this relation, that you can change the intersection with the sum and vice versa, and then you get another relation. But these are important distributive laws, and we usually want to be able to say that we have some distributivity in our models, and it depends on our design matrices. And then we have a modular law, which is basic for linear spaces, and this is it's for any linear space, and it says that if C is a subspace to A, then A intersected with B plus C is A intersected by B plus C. But remember, this is only true for a subspace. So you will see this distributivity because I just written C here, but C is a subspace of A. I could also have written A intersected with C here. And then we would have a distributivity. So under this condition, we have a distributivity. But this is always, it's true. And this is also, if this is true for lattice, you say that the modular lattice, and this is has been studied pretty much. There are these modular identities also. Here it is A intersected by B plus A intersected by C, and then this is always can be written in this way. But it's not the distributivity. It's not you see that you need to have this A intersected with C inside here. You cannot have C just here, because then it will not be true. If it would be C, this would state a distributivity, which is not the case. There's another bit special here, that is a median law. I will not say much about it. It's just how you can combine spaces. If you have three spaces, you can write up relations like this here, and it's not so commonly used, but it is of use. Here we have some kind of cancellation law, called cancellation law, and that means that if A plus B equals A plus C, and the intersection A with B equals A of C, this gives that B equals C. And you know, this algebra is good because if you work with matrices, for example, then we usually prove these things by also looking at ranks of matrices. But this is not needed. We just need this type of knowledge about relations, which stems from the lattice structure. And in some way we could, because when I was young, one talked a bit so much about coordinate free or it depended on choice of basis when we did our statistics, but here this is completely coordinate free. It's just about the main structure. There are some other concepts which are important, and this is, for example, we call disjointness, orthogonality, and commutativity. I will just very briefly mention it. First, we need what is orthogonality here, and then we call it orthocomplement. And this is any matrix where you need to have an inner product, and then you define it in a certain way. Like you can just say that it's like a vector which is orthogonal to another vector according to an inner product. And if we accept that, we have a number of conditions here. For example, that A intersected with the orthogonal complement here is 0. They sum together to the whole space. And since these are finite dimensional spaces, so if you take the orthogonal complement of an orthogonal complement, you will return to the original one. There is well-known De Morgan's laws that if you take the orthogonal complement of an intersection, then it equals the sum of the orthogonal complements. This dual statement also. And there is about this monotonicity or antitonicity, that if A is a subspace to B, then the orthogonal complement is the subspace of orthogonal complement to B is a subspace of orthogonal complement to A. And this relation one is using when one is working with linear models. So, but we see simple expression. All of them they're very simple to prove out from the definition what it is. And here also I didn't say this is about disjointness. Yes, since the sections here, if you have many spaces, it's not, one can define disjointness in a different way, and here's one way to do it. But there exist alternatives. If you have two, it's just that the intersection should be 0. Here's always the intersection with the sum of all other spaces should be 0. And then for all indices also. And if we have this orthogonality, we come into a class also what we can call orthomodular lattice or subspace classes. And there are books written about these classes. So here we have, and this is maybe the most important, that is A is a subspace to B, because we want to decompose our spaces. So if A is a subspace to B, then B can be written as A plus and its orthogonal complement intersected with B. So this is a way to decompose the space B. And then we come back to commutativity, but it's so that if A has this distributive property, one can turn around it and say also that B has this property, and means that you just switch B to A. But we return a bit to commutativity because this is maybe it's a pretty fundamental concept. But here are some more decompositions. So we have like a space A, it can be, we have a subspace here, and plus this orthogonal complement and intersected with the original space. So this is how we can decompose an A matrix, and here we can decompose the sum into two parts, and here we can also start to decompose the orthogonal complement in a certain way. And we can do it here. Here we have a whole space, and we can decompose. And here is not an orthogonal sum. When we do it like this here, we do it because one does it in two-step, but it's the usual sum of disjoint spaces. but they are not orthogonal. And sometimes you can, with three spaces, when have another type of decompositions. And all these decompositions can be useful in certain applications. And commutativeness, here we say that the spaces are commuting, denoting that AI bar AJ. If AI intersected by AJ is sum or plus AI intersected with AJ's complement, if we then come back to AI, then we say that spaces commute. And here we can see that we have some kind of distributivity going on. We intersect with another space, and it's also a complement, and we return to the whole, to the original space. Maybe one of the most important relations, there exists an enormous amount of equivalent relations or characterizations of commutativity. But one very interesting is this relation where we have a so-called geometrical orthogonality, and which means in some way that AI and AJ should be orthogonal if you remove what is in common. So you're removing what is in common is by taking the intersection orthogonal on both sides, and then AI and AJ should be an orthogonal. And this is in some way, you can say that two, but there are many applications of this, and the term is nice. And I want to say, if you have like two areas, and they are orthogonal, geometrical orthogonal, if what is in common, which is a line, maybe, if you remove that line, these areas can be orthogonal. And this gives you a nice interpretation, a pretty useful interpretation of geometrical orthogonality or in particular commutativity. Then the name commutativity, the interesting thing is that, or interesting is good to know, that it's connected to projections. So, and there are AI and AJ and commute. If you have spaces here, AI, we have the intersection by AI and AJ. If the projection of PI of PJ commutes here, so you PI PJ with PJ PI, then we say that then we have that the spaces commute. So here we see this commutativity. And an implication of this is here that the intersection, which we want to take the orthogonal complement on, for example, the intersection is just given here. It's the product here is given by the intersection. And therefore also we can see that it doesn't matter in which order we project here. We have some relations here that if A is a subspace to B, then A commutes with B. If A is orthogonal to B, A commutes with B. And A commutes with B implies that A commutes with its B's orthogonal complement. And then we have this symmetric, what we mentioned before, A commutes with B implies that B commutes with A. More important is, and so on more, it's pretty interesting that we can decompose whole spaces. So we have a set of spaces, subspaces, n in this case, and then we can decompose, for example, in this way. It looks complicated, a lot of intersections and sums and whatever, but it's possible. And from a statistical point of view, the trick is, of course, to understand these subspaces. You can decompose it in this way, but it's not sure that these spaces which are generated here are interpretable. A bit more here is that we can look at tensor products, because we had a previously Kronecker product, and it will be shown that, or I will just indicate that the Kronecker product of two matrices is in some way a tensor product, or the column space of the Kronecker product is a tensor product of two spaces. So if we look at tensor products, I will not say really how it's defined here, and there exist simple definitions for it. So we have spaces here, and then a tensor product of A and B is 0 if and only if one of them or both are 0. It's a subspace here if both are a subspace, like we have marginally, and a subspace, and then this implies that also the tensor product has it. And then we have some other well-known relations for spaces. And if you would think about this as matrices, you would see exactly the same expressions for matrices and Kronecker products. And maybe most important is here that you have the two tensor products are the intersection of them is 0 if and only if one of these or both marginal intersections are 0. If you look, and then it starts to become a bit more complicated. If you look at the tensor product of the orthogonal complement of a tensor product. So for example, here we have that this is orthogonal to this part here, and this holds if and only if marginal orthogonality applies. We can also see that the tensor product, its orthogonal complement here, is given here by 3 spaces, or you can combine some spaces, you get 2 spaces. And then at the end I have some decomposition also, but this is not so important. I think this is the most fundamental, what you see here. And we can do it even more complicated, that if we have a sum of 2 spaces, we get this. And yeah, these decompositions, which can, spaces can be put together, so we have less spaces to work with. And at the end, everything depends on if this should be useful, there should be some interpretation. And one can generalize this here to arbitrary, but then we have to require some nestedness. So if we have nestedness, we can decompose the whole tensor space here in a pretty nice way. And usually we don't do it with working with linear models or multivariate models because it's so much notation, but in principle one can do it. So if we want to extend the sum of profiles models from 3 to an arbitrary number, one can use technique from here. And yes. If you think about commutativity, that the two tensor products commute if and only if they marginally commute also. So we can first apply this here to matrix equations, what we have done. So a matrix equation is here we have a linear equation in X. So we want to solve this here, and then we have, if this should be consistent, we have to suppose that B belongs to the column space of A. And now we start to come back to these column spaces again, because these are matrix expressions. And then there is a classical solutions, for example, that we have generalized inverse of B, because we know that every solution consists of a particular solution, and then we have a solution to the homogeneous equation system. And a solution to the homogeneous equation system is, for example, given here, and is a classical solution. I will argue a bit that this is maybe not the most natural way to express something, but this is anyhow given a general solution. So it's written once more, but we could replace this here by just saying we need any basis vector or matrix in an orthogonal space to the column space of A transpose. And then we could replace this part here by AO or A prime O. And the advantage with this is that here in some way that we know we have restriction on X, but still the Z is of has the same size as X. And this is in some way unnatural, I would say. So, but with this choice of basis here, we would get, say, appropriate number of free elements. Because these sets, maybe didn't say it, but sets indicate that elements are free. So if you look at matrix equations, we have this AXB equals C, and then we have more complicated when we have two equations of this type, and then we can also handle things with the sum of these, say, profiles. It's worth to remember that for 3 equations, this technique will not work. So it's pretty limited to 2 equations, and it's still complicated. I just first show you the solutions here to this equation here, and we have a particular solution. I will not give it, but it's in fact the generalized inverse of A times C times the generalized inverse of B. But here we have the solution to a homogeneous equation system. And sets here are arbitrary matrices. These generate orthogonal complement, and this can be reduced to these 2 expressions or some alternatives. And the idea is here, or why do we have 3? Now we can go back now to them. And our tensor product, I mentioned that this here, the column space of the Kronecker product is in fact a tensor product. And then we had a relation, we are interested in orthogonal complement because you see here, this equation is equivalent to this part here. So we want to have the orthogonal complement to this part. And this is given here, and then we use this result we had before, so we could have 3 spaces here, or we can combine a bit here so that we get 2 spaces. For example, if we combine these 2, that one and this one, we will get the first one, and then this stands here. If we combine these 2 here, we will get the last one here. So there's a different possibility to combine these spaces. And using this expression here, we can say that the vec is of this form, and then we can convert back it so that one gets expressions of this form here. So these are about matrix equation and the decomposition of these orthogonal complements. And here it was in fact this theorem or this result we used here. This was a tensor product. It could be decomposed in this way. And here I indicate also that the column space of a Kronecker product is a tensor space of each marginal or of the marginals here. Just look a bit, if you look at the matrix equation of this form here, it becomes much more complicated because the spaces are more complicated to decompose. And here I just give some different types of solutions, so they're very similar, but here's a general solution. I have merged terms. The sets here are arbitrary matrices, and then we have these basis matrices T's and S, and I have given them here that T should satisfy this relation here, and S should satisfy this relation. And then we obtain the solution here, the general solution to this system. If you just look at the growth curve model, we see that, or growth curve, sorry, the linear equation AXB equals 0. And what we did here when we solved this equation, it was at looking at the orthogonal complement here from a tensor point of view. And this is given by these spaces here. So by using the basis of these spaces, we could immediately set up the solution to this equation here. And it's the same for the more general when we have two profile equations. And here for the profile equation, we don't need to have any nestiness. And so previously we would have, if we have several equations, we would have a stair structure, but this is not the case. So we can have cut out something here, and we can, or something which doesn't impose some kind of stair structure. And finally, I will talk a bit about some projection. We are talking about projections and spaces and a bit how to operate with them also. First is a useful relation for expressing an intersection of subspaces. If you want to work with it explicitly, one can write it in this form. And here, of course, this O means that this is any basis in orthogonal complement to the column space of B. And this is a basis to this orthogonal complement to A prime B O. The projection, which we mentioned before, these are, maybe didn't say it, but it is the idempotent matrices. And then we are interested in the column space of when we are projecting something. So the column space of when we are projecting A, it means we operate PA, it is equals the column space of P intersected by the sum of two spaces, the column space of A here, and the column space of P transpose orthogonal complement. Or it's maybe better, or most people maybe say that the null space of P should be here. And this is in some way not so good, what we see here, that we have a sum of two spaces. We want to project, but this sum means always sum was more difficult to interpret. So in some way we would have been very happy if we would have seen a result like this here, that the column space of, when we project P of A, this is the intersection of the column space of P and intersected with A. But this is only true if this relation holds here. So it's not just that we have found a projection doesn't mean that it's so easy to operate all the time. And here is almost to the end of this part here. Here are two relations which I'm using very much when we're working with linear models. Here is also projection, as you see, these are idempotent matrices. This is, by the way, I have said it, generalized inverse here. These are these matrices spanning orthogonal complement. C is defined on any matrix satisfying the intersection of these spaces. And then we have a very useful relation which takes care of most linear models relations, in fact, when we're testing, when we're estimating, at least when we connect it to least squares. So these are, so we understand we have some kind with unrestrictions, with restrictions. If you want to combine it in some way like this and this here, then we get the whole space. The special case which has been used very much is to look at the these projections. So we have a projection here with BO, S, etc. S is a matrix which has an effect on the inner product. And then this relation here, this is a projection of orthogonal complement. This is equals this idempotent matrix. Now also the S is on the left side, or the inverse is on the left side compared to here. And this is in some way a projection on a dual space, but this I will not talk more about. So if you would multiply both sides with the S inverse, you come to this relation here, which many authors have been using many times. But the fact is that there exists this generalization from this relation to this here, when we can include another matrix A, not have a B, and even C, but C is a function of A and B. Some more decompositions, but it when we decompose linear models, that is a sum of two spaces here. In particular, when they have a singular covariance matrix, one can use this here. And yeah, and if there's a subspace instead of a sum here, we just have the column space of A, we get the right sign. And here decompositions for with projections involved and for the whole space. And then we see that one can do it, but they become complicated. This B1 and B2. And then we have this projection also here. This is relatively easy to understand what it is. So this was part 2, third part. And that will be some kind of applications on the growth curve model to a bit non-standard situations where spaces and decompositions will be put into focus. But we refresh our memories from the first part and see about the growth curve model. We sometimes call Manova or bilinear regression model or sum of profile model or just a profile model. And it's given here. So we have observations y now here, which later will become x, but let's go around, we say y now. So y is p by n, we have a design matrix A, p by q, we have a with an this is a with an individuals design matrix, and here the C is a between individuals design matrix, where we have often treatment groups. Unknown parameters are given by the B matrix here, and in the error term, we have an unknown dispersion matrix, supposed to be positive usually. And we have the likelihood given here, and we have the, if you want to maximize the likelihood, the normal equations are given here, or likelihood equations. And we're going to solve this now. Previously I just showed you the solution, but now we'll show one way of doing it, which we will use later. And you see here is the first equation. This you obtain, say, when differentiating with respect to B, and that's given here. And this equation, in fact, is equivalent to this equation. That means that we have a put in C prime here as a projector, and then at the end also we have removed this here, which is not so essential, but it follows that we can remove it. And then we have our equation obtained by differentiating with respect to sigma, or sigma inverse, in fact, given here. And this can be decomposed in two parts, and this follows from our decomposition of linear spaces. So we have these two equations. We see it's a complicated equation in sigma and B. It's non-linear. We have a sigma here, and we have a B here. We have sigma and B here. So this is by far not linear. But if we pre-multiply this equation here by A prime sigma inverse, then we will obtain a relation which is because sigma inverse cancels to sigma, we get A prime here, and then on the other side we get A prime sigma inverse times S here, and then this the last term, when we have A prime sigma inverse here times this, then from the first equation, what we have here, that should be 0. So when we solve this term here also will be 0. So then we have this relation here. And if we have this relation, we see that we can replace A prime sigma inverse here by A prime S inverse. Once we have done it, we have a fully linear or bilinear equation in B. And this can be shown to be consistent, and we have a solution for it. And we have a solution for A, B, C also. On that solution, if we insert it, plug it in here, then we have also an estimator of sigma. And altogether, the maximum likelihood estimators are given here. So for this bilinear model, we have the estimators here, and then when the inner product has been replaced by S or S over M, the constant doesn't matter because it always cancels. So, and here we see the norm relation which are obtained through projections. And we can see that S is Wishart distributed, and the last part here is normally distributed, so there's some kind of mixture between normal and Wishart distribution. But this is a complicated expression from a distribution point of view. And so one has to approximate it in some way, but this we are not going to discuss here. If you look at the spaces again, we have this for the growth curve model. What we have solved, we have these different variations which are involved in the estimation of sigma. And we have the mean space on which projected on. For the Manova case, we just projected on the whole space here, the mean space, and that one didn't have to take into account that there is an inner product defined by an unknown covariance matrix. And the estimation process, now we solve linear equation, but one can also view it that we first estimate the inner product with the help of this part of the space, which leads to S. Insert S or replace S instead of sigma here, and we come to this expression. And if we want to estimate the mean and sigma, we just do it through usual projections, and we obtain the maximum likelihood estimators. We can do it with restrictions. We can put restrictions, and this we come to this structure, and we note that this is not the growth curve model; it's an extended growth curve model. And then we can do the same way. And in general, we have this extended growth curve model or sum of profiles models where we have M profiles and they shouldn't be estimated. But the important thing is that we have nested subspace conditions here, nested subspace condition. And this means that we have a stair structure from that. You see, this is nested inside here. Without that, if we would have some empty spot here also, then we would not, then we would be in so-called seemingly unrelated regression models, and there's no explicit maximum likelihood estimators. And here was the procedure how to estimate it. I will not repeat this. Just give the final estimators is for the parameters, and we have the Z matrix because we don't put any full rank conditions now. But we have a unique estimate of the variance almost, which is given by the help of projections. And this is these projections are given here. We have some kind of sums of squares matrix, which is an updated sums of squares matrix with the expressions, for example, S3 is a function of S2, S2 is a function of S1, and S1 is given here. So this is just these expressions are obtained by this sequentially projections which takes place. And the same with this Q1 is just a function of A1, S1. Q2 is a function of Q1 and A2 and the updated S2. And Q3 is from Q2 and Q1 and S3. And this one can generalize to M profiles, in fact. Later on, I'm also going to talk about the Manova model, which is given here. So now we come to our first application, and this is to talk about partial least squares, and I want to connect it to the growth curve model. Partial least squares is an old idea which they belong to some kind of ideas by Hermann Wold about soft modeling. It came in the 60s already, and this is still a very active area. One has generalized it in any direction maybe. But I wanted to tie it to linear models theory, because in some one is applying linear models, but I'm not sure. But mostly these things are algorithmic, and but at the same time it's just about projections, everything, and I will try to explain how I look upon it at least. So I will in some way. I will not say that I will do exactly the same, but I will put up models and seeing which give exactly the same PLS solutions which the algorithm are provided. Then one can discuss, of course, if the models are relevant or not, but this I will not do today. So the basic setup here is that you have explanatory variables x and you have a response variable y. And then these explanatory variables or background variables, they are correlated. And the problem is that if you have many, that there can be collinearity among them. Means or near collinearity, not exact. Near collinearity, which gives problem in estimation and to produce good estimators. So the basic setup is that xy, we have a mean here. Normally, this is one dimension, this is p dimension, or size p, size 1. And we have the covariance matrix sigma for x. We have a covariance or dispersion matrix, and then we have the covariance between x and y, which we call omega, and we have a variance for y. We will not think about all of them as unknown. We will suppose that omega and mu y and sigma y are known quantities for simplicity. But this is more about understanding it. In reality, in practice, we can of course include estimate, plug in estimators like moment estimators or any other type of estimate, robust estimate and whatever instead here. But we want to see it, the structure here. So the algorithm is in some way pretty, it was a long time ago one invented it, but it was difficult to understand what was going on. So in some way one starts with residuals and then one creates scores and with the help of this omega. So the algorithm goes from 1 to up to when we have a stopping rule, A. In theory, there is invariant space, which it stops, but this we will not talk about. We have some scores, we have weights, and the important quantity are these weights here. Everything depends on the weight, I would say. But in the algorithm, it constructs scores, weights, and then determines some loadings, we call it. And then it defines new residuals. And then it goes on until it stops. You can express x in the following way. This is how one creates it. These p's and t's, and then there's an error term. So it's not a random error term, it's just a model error. But the algorithm, in fact, this is very similar to a Gram-Schmidt orthogonalization procedure, what is going on. So we have different because one takes into account some kind of updating of the covariance. So, but it's really projections which are involved. So you can get next, say, omega, these are bases. You get the basis for a plus 1 from A by just the projection. This is a projection on idempotent matrix. And you can update here also with the help of an idempotent matrix and multiplication, or with the help of this basis. What I'm claiming is that the basis vectors here, this GA, I call GA, is in some way, it can be the partition matrix given here, or it can be any other matrix generating this space here. I will talk about this space because that is fundamental. So if you talk about this expression, we can immediately generate it by knowledge about these omegas. So we can generate the next dispersion here and the next omega. You will also see these projections, how it comes in. And the omega 1, which we have here, is just the original covariance between y and x. So now the important observation is that these bases, they form a Krylov sequence. So this is a Krylov space. It's a polynomial expression in sigma, what we find. So the algorithm generates a basis, but the space, and it's always the space which is interesting because I will show you later that we are going to regress on this space. This space is given by this Krylov space. and it stops when we stop A at some point. So here's the final. When we want to predict Y, we're using this type of predictor where we have GA involved. And this is in fact the least squares predictor in a certain sense, and we return it. And usually one standardized, one has mu equal to 0. Then if you want to work with real data and not just insert, we have to take into account this mu and this or the means. So these are given when we take into account, we come to this expression. And then one has to estimate this mu x and mu y, for example. Okay, now we do a little bit different. This was an algorithm. Now we start again from scratch, but we just look at the explanatory variables. Let's say that the explanatory variables follow this model here. So here we have a strange, we have this GA, which is this basis Krylov space, basis of a Krylov space is given here. Here are unknown parameters, and we have an error term where also sigma is included. The dispersion of this epsilon is sigma. And we have also the same sigma is included in this expression here in the design matrix. And given sigma, least squares predictor is given here, or prediction of x. So we predict here, and this is by projections going on, we predict them here. And then we can see that if you want to predict y, we use, say, a conditional mean, which is given here. So this prediction is inserted here, and this is identical to the PLS predictor. So now we started with GA and X, but we can do a little bit different also. And I will try to explain. Can call it even a semi-population PLS, what we are doing, but I will not talk so much about it. Okay, now we think about that we have observations, and we will find explicit likelihood-based estimators. They're not maximum likelihood estimators, but they're very close, I think, to maximum likelihood estimators. Because usually in literature, one is just plugging in estimators, and this can have some drawback. And usually this seem, or I will show you some. Later we see with data, but how to insert with the growth command. But we have to do something first. Now we start the model, and this one can then, of course, wonder if this is a good model, that the explanatory variables, the mean there is proportional to the covariance between y and x. And this is of course a bit, one has to think if one believes in this or not. And then we have an error term where it's about the error in x. And then we predict y via conditional expectation. And the problem is of course with this sigma inverse, because here we have, if you think that we have a near collinearity of the x variables. But this is that we have a model, we predict in this way. So far we have no observations. Okay, but what to do with the sigma inverse? Now one way to think about, or one way to approximate it, is to express this inverse as a polynomial in sigma. This can be done through the Caylor-Hamilton theorem, and we say the sigma inverse is given here. And here Ci is a function of sigma, but we will completely forget it. And the approximation which will take place is that if this is of size p by p, then we will express it instead of p components, which gives an exact approximation, we're only going to use a smaller than p. And of course, this can be questions because it's not like a tail expansion that you further away and from the original, so less a than p, that the remaining p minus a terms are not of any importance. This is not true. But this is like a multivariate linear or not multivariate and multiple regression model. Then you use this as an approximation of something. It doesn't mean, so you still can get a good approximation of something. And this is, if one often compares the PLS with PCR, this is in some way, in PLS you give it, in PCR you're much more strict that you give it that there should be some kind of eigenvectors involved. But here is more, eigenvectors can be involved, but there can be also other functions involved. And so in that sense, it should be a bit better to use this type of approximation. It's only an approximation. And if you would have important impact from higher, from C, I, which is for I, which is larger than A, then of course this approximation is not good. So what's going on? Here we have our model. This can be written like sigma inverse here. Then we approximate sigma inverse. And then we see we come to the approximation here. Here was the exact expression. We come to the approximation. Ci is including gamma, some unknown constant. And then we just put that as a beta. This will be our parameters. Also in reality, sigma I should be a function of sigma. But we just call beta, and we are going to model that separately from sigma in principle. And here we have our GA, this Krylov space which comes from here. And this we can call A beta. A is given here in some way. And here is this GA, which is polynomial. And then we can of course think, why does this make sense? In some way I think one should understand if this is appropriate. If this is appropriate, then maybe the whole thing works reasonable. If this is not appropriate, then of course we come completely wrong. So this is just to summarize what we have done here, nothing more. And now we go to data. Data is that we have each x, if we, in this matrix, if we think about the small x which we had before, put them side by side, we have n observations. We have for each x, we have a model A and beta here, but now since we have many observations and we can even have a design on the observation, different treatment groups and whatever, we have a C matrix here. So we have A, B, C plus R, and this is the growth curve model. It's just the difference is now that this A has a very complicated function in sigma, and sigma is also involved here. And we want to estimate, say, the mu x in order to predict. Here's a prediction. We want to estimate mu x here. And mu x, if we're given sigma, it's given here. It's just projection. It's a usual projection we had before for the growth curve model. Because if sigma is known, it's just a linear model here. So we do this projection, and then we have an estimate of mu if we assume omega to be known, and if this is supposed to be known also. And then we have a prediction given some new observation, XO, and then this indicates which design we have. If we only have one group of individuals, all the C matrix will be 1, and this will also be 1. Okay, so what to do now if sigma is unknown? Here's the result. And we had sigma when it was known. We have sigma here now, and now we can replace sigma by S. And we have to think why this works. Even in A, we can replace sigma by S. And it's not just a plug-in, as you will see. And then we have our estimate of the variance. So what is going on here? We have here our likelihood is proportional to given here, and really able to maximize, but we will maximize it partly, I would say. Sigma is involved in A. So if you remember, here the growth curve model. The variation we had were here, and we have also sigma included now in A, and as something which generates or steers in a product. We have the mean space, variation space. So if you look at this here, from here we could also work directly with the likelihood. We would come up in estimation equations, for example by differentiating the B, or by just looking at this here by projecting. We have this estimation equation for B as a function of sigma. And then how should we estimate sigma? Now the natural way to estimate sigma is to look at the variation data. And the variation data is fully described here in this tensor space. So then we say that n sigma equals this type of variation. And then we have a sums of squares matrix, which we used before to estimate the inner product. But, and it's still used, it's given here. And the point is that this is an independent of sigma and B, this expression here. Just an observed value if you would include data. So, this expression here can be written out. We have the S here from this part, and then I have this part here, and this is given here, the second part. Something orthogonal to A. So sigma should satisfy this expression. And in fact, sigma is also included in A. So this is a pretty complicated expression. But as before, we do it when we wanted to find the estimator of the growth curve model. We pre-multiply it by A prime sigma inverse this expression. And sigma cancels towards sigma inverse, so we just have A prime here. We have A prime sigma inverse S, and A prime sigma inverse times this here equals 0. This is an orthogonal projection towards A. And if you use the inner product here, sigma and A prime, this will just be 0. So we have this relation here. And we're going to use this because sigma is still involved in A. So if you really write out what stands there, then for A prime, we have this expression is a Krylov sequence. We have the transpose of A, so omega prime sigma up to omega prime sigma. And then here we multiply A by sigma inverse, so we just cancel one here. So we get omega prime sigma, blah, blah, blah. And then we have S here. And so we have what stands here is in fact this relation. And then we look closer at this here. And you see the first row here is omega prime equals omega prime S. Omega prime sigma equals omega prime S. Second row says omega prime sigma 2 equals omega prime sigma times S. But omega prime sigma is obtained from the first row, which is 1 over n omega prime S. So for omega prime sigma square, we have this relation here. So we can continue like this, and at the end here, omega prime sigma A, it can be written in this way. So omega A is 1 over n omega prime SA. And that means that we have a full knowledge of A, because A is a function of omega are given here, this Krylov sequence. So we estimate A in this way. And we also know that the expression A prime sigma inverse equals this one here, and that will turn out that we have for our, if we now go back very much, here we see that, and no, you should see if I can, sorry, it will take, we have an S here and we have sigma inverse here, and we know that our A prime sigma inverse should be replaced by A prime S inverse times n, but n cancels here, so we have also estimated sigma here with this procedure, because we know this here, or we know that we can estimate this by this here. So then this result, so we have a good feeling that these estimators here, they fulfill natural conditions. It's not fully maximum likelihood, but the numerical calculations we have done means that they're pretty close. So at the very end, we have estimated our parameters and then we predict. It's given here, and we have the estimator of mu x is given here, and this estimator we derived before. Now, finally, we'll very briefly look into another type of model where we have some reduced rank restrictions on parameters. So this is a Manova model or growth curve model, Manova model. He is a growth curve part, he is a Manova part. So we have this picture in these spaces, and this model can formally be written in this way. And with the reduced rank regression, we say that we will put reduced rank regression on B2 now. We put some restrictions, but these are not in space. It's just a rank. So in some way, we just put the restriction about the dimension of the space, not what space it is. For technical reasons and because we want to connect it to an extended growth curve model, this assumption about F and C has to be assumed. Here are the sizes of matrix, but the most important is that the rank of psi is smaller than P and this K2, so there's really a rank restriction. Otherwise, we have the usual conditions as for the growth curve model and extended growth curve model. It's a bit difficult to interpret this rank restriction, but one way of doing is to know that if you have rank restrictions on the matrix psi, you can always write it as psi1 and psi2. It's not so clear what these are, because you can have restrictions on the columns and on the rows with pretty different meaning in our models. So there's some work to do how to interpret. And there's also not a unique decomposition, so sometimes I put some extra restrictions here, but we are not going to do it. I'm also thinking about that if the rank is R here on side 2, that latent processes, which we have very little knowledge about. It's just that we observe something in F, but F, it can be weather variables, and we can measure temperature every hour or more, but there are few number of latent variables which affect some response. For example, if you look at crop growth, you don't need to have, don't know or need to know the exact temperature every hour. It's something else. It's just a background information, or we should summarize it in a nice way, which we don't can model directly. So then it's interesting that when some kind of soft modeling here also, that we just put rank restrictions, and it's pretty objective. So we have, without rank restrictions, we have our Manova model. With rank restriction, we have some restrictions on the mean space here, on the Manova part. It's a bit difficult to say what it is now, but it's in fact now, it's not clear from the beginning because there's no really spaces involved. We just know that the size or the dimension of the space is smaller than this one here. This is what the rank restrictions mean. But we are applying maximum likelihood theory, and then we will identify the space. And this is a maximum likelihood approach which is doing it. It's not the model from beginning. And you can see here are the spaces, and then if one estimates things, it turns out that we get a maximum likelihood estimate of psi1. I will show you a bit how it works. And then once we have that estimator, we have fixed the spaces also, and then we can project. And then we can, for example, also discuss residuals and different meanings of residuals and check models and and estimate the variation and all the things what you're doing with residuals. But it is a maximum likelihood approach which gives us this possibility because it will fix the space. So I will just show you here how this is going on. So here we have the model. Here we included the rank restrictions. So you see that it's not a bilinear model because both psi1 and psi2 are unknown. But still, when we estimate, we will fix psi1. And then we come to an extended growth curve model because this column space of F transpose is included in the column space of C transpose. So we have this space or this assumption, this model, we have the likelihood here, and then one can see, yes, by some inequality, which is that this is an upper bound for this likelihood is given here. And we should, and W is given here. And W still consists of unknown parameters, B, psi1 and psi2, and they have to be estimated. We should find estimated so this upper bound is achieved. And the upper bound is achieved if and only if sigma is equals W. So when we know B and psi1, psi2, we know also sigma. This is maximum likelihood. And there are pretty many calculations. I will not show you. I just show you a pretty nice trick at the end. And when we manipulate the determinant, and in fact we want to have a lower bound for this type of determinant. This we don't have to worry about. There's no parameters, but we have parameters in Q, and this is the unknown psi1 because everything up to here, then we have used knowledge from the extended growth curve model. So now, if we are able to estimate psi1 here, then we have all estimators. So then we have the determinant of this Q transpose UQ. And we see this is a complicated function in psi1. U is not a function of parameters. So we want to find an upper bound, no, a lower bound of this quantity here. And the lower bound is given by an eigenvalue theorem or the Poincare separation theorem that this determinant is lower bound of this expression where these are eigenvalues of U which are not do not depend on any parameter. And then we see equality holds when Q consists of the corresponding eigenvectors to U. So the corresponding eigenvectors we label them V1 to VQ2, and we call K tilde. So then a definition of K, we can set up, here is the definition of K, and now we say we estimate K tilde with the help of the eigenvectors, and now we should find psi1 so that we can find this estimate. It looks complicated again, but it isn't. A direct expression is given here. So the estimate of psi1, because H doesn't depend on any parameter. If we use H1 here, or H transpose H inverse K tilde, the eigenvectors, insert this here, you will say we get rid of H from both sides, then we will have K tilde transpose K tilde inside, but these are eigenvectors, and I should say that we have standardized eigenvectors, so K transpose K equals the identity. So this will be the identity, and then we see that outside H prime, this here is cancelled, so then we obtain K tilde. So then we see that psi1 is the solution to this equation here. And then we have at least one maximum likelihood estimate. Maybe not all. And this I don't know really today how it is, but there's one estimator at least. And then one can estimate the psi when we combine it. The whole part here is given here. And then as you can see that it starts to be like projections again, which are involved. And here's the final result here. And this is for sigma. We have T1 is here, but in T2 we have this psi1 estimate, the eigenvectors. So from a distributional point of view, it's also complicated. And here is the final and mean predictor or the estimated mean is given here. And then we see that this here are really projections. It's only projection, but this is a method which is doing. So very final, I will just mention another application. Or by the way, here is this figure again with all these residuals and given here, and we can explicitly write them out, and we can interpret them through these tensor spaces which we had. Then we can see if where things deviate, what is not good in the model, etc. Okay, now we're doing a bit different. We look at the growth curve model, and then we have rank restriction on B, but also on sigma. So we have a singular sigma now. They're given here. So if you think that we have rank restrictions, we have rank restriction on the mean here, it will cut off a bit part here. And then we have rank restriction sigma, which means that we have done the full space here now. We are in some kind, I don't know, geometrical, maybe it's cylinder, and it's definitely not the full tensor space. So it's some subspace, and one has to be a bit careful about it. We can decompose the space by orthogonal component where the column space is something which is orthogonal but is included in the sum of the space of A and sigma, and then we have the orthogonal complement to both A and sigma. And A is a mean space in this case. And we can have just an expression for this subspace which we had here. It's given here. These are eigenvectors to the corresponding to non-zero eigenvalues of sigma. So they are semi-orthogonal. And then if you do a one-to-one transformation or one-one transformation, also sigma is unknown, but we can do it. Then we will get here, we have the space. This is a full rank, this matrix. And or full rank, but we can choose bases so it's a full rank, but we can multiply this by x here, so we will get 3 equations. These equations are given here, and then you can see 2 of these equations are orthogonal to sigma. This is orthogonal to sigma, this is orthogonal to both A and sigma, and that gives some interesting equation in fact. So when doing it, we have here and a linear model. E equality is equality in distribution. It's just that we bit unusual that we have a gamma here, which is unknown. But then we have the second equation where this is an equation, not it holds in probability 1, because the covariance of this expression equals 0. So this is the mean of it, and then we see that we get some kind of restriction on B. And then how should we interpret x here, or this part here? And then we have also that the x should satisfy this part here. So we have to assume a number of things now in order to continue, and how to do it. I would maybe start to do so that I insert observations here, xo, and here another observation, and say that this satisfies. If you don't satisfy this, one has to project on certain spaces. And the same here, we should think about this as a linear equation system. I don't know anything else. So then it's for, if this is valid, or it has to be valid, it means that this x should satisfy certain conditions. So we have to project it also, because if you simulate it will hold the middle, but if you don't simulate, just have data, one has to have some pre-processing and make appropriate projections of the data. So then we get B as data, and data, there's no randomness in it, it's just a constant. And then this constant can be inserted here, and here we can treat it as usually rank restrictions on some model, or we'll see that we are able to estimate the sigma. So this is some kind of, here we see some kind of reduction on the mean space also. And it can be useful if this is another way to put restrictions on B by supposing that sigma is singular. We could in principle say that sigma is of rank 1. And then we could see that we get the model here, a univariate model, which will work. So it depends on the situation, and it's particularly useful if we don't have so many observations. And we have done some simulation, and it seems to work pretty well. So that was my talk here. So I thank you very much for this attention, and you are always welcome to ask questions now after maybe, but also write me or phone me if you can, and whatever. Just nice to cooperate with everyone who is interested in these topics, and there are definitely a lot of open questions here. So once again, thank you very much.
Thank you very much, Dietrich. That was quite a performance, I must say. I hope you enjoyed it as well.
Oh yeah, this was a big event to me. I wonder who was doing all these things.
That is a memorial lecture. Yes, you had not done this by overnight, these slides, I can tell you. It had taken a couple of extra weekends. Yeah, no hesitation. Maybe you must know the paper by Jerzy Paksalari. He had 47. Pardon?
Yeah, it is a hard work.
Yes. Okay, so we are running a bit late, aren't we? By schedule. I wonder that do we have time for one or two questions? Because as far as I understand, we are a little bit late. I don't know how this.
Seems like a coffee break.
That's
Can you hear me?
Yes, sir, we can hear you.
Can you hear me?
Yes, sir, we can.
Okay, come. Is it done?
Okay, I propose thanks to Dietrich, and then we can. Yeah,
there is some problem in my network. 1 minute.
Well, thank you, professors. Thank you very much for joining us.
Thank you.
Thank you. Without no further delay, let us move to the next session. So in this session, we have two speakers. Professor Augustin Markiewicz from Poznan University of Life Science, Poland. His areas of interest are matrices, algebra, linear algebra, statistics, applied mathematics, regression modeling, linear models, design of experiments, many more. Today we will be talking on the topic covariance matrix estimation based on matrix projection. Another speaker of this session is Professor Martin Singel from Linköping University, Sweden. His research interest is multivariate statistics, focusing on multivariate normal distribution with the pattern covariance matrix. He has also considered a growth curve model with a linearly structured covariance matrix. He is also working on a conical structured covariance matrix, which leads to a matrix normal distribution, or more general, a tensor normal distribution. Today we will be talking on residual analysis for geometrical Manova and Manova Model. To moderate this session, may I now request Professor Beatrice van Rosenkrantz, Swedish University of Agricultural Science, Sweden. Over to you, sir.
Yeah, do you see me? Do you hear me?
Yes, sir. We can hear you, and we can also see you, sir.
Okay. Yeah, I don't know. I just would welcome Augustin and all the friends. Hello.
Sir?
Augustin. Go on with Professor Augustin Martinez.
Hello, I'm here in a different system. I was trying to talk to you through my system, but I couldn't reach you earlier. Just I wanted to communicate that Augustine as well as Single, those two are the speakers. No? Somehow we are not in a position to reach them. Don't know the exact reason, whether our mail has reached them or not. But I'm sure it was scheduled long back and it's with them, and for some reason they haven't yet come. I wanted your session. Shall we start their lecture? They may come and join in between.
Sorry, I couldn't follow it.
Yeah, I'm asking your permission for starting their lecture. They may come in between. Somehow they did not join, but they have given their lecture, which we can play.
I'm really sorry. I don't. There's no lecture, but
Just check whether they have come. Join. Sure. They're not good. Maybe
we should ask for Martin Single.
yeah, in my session we can play their lecture. Yeah, I want to take his permission before.
Yeah, no, take over, please, because I hear so badly here, Sweden.
Yeah.
Decide what is best to do.
Yeah, we will start with the Augustine's lecture. Augustine is the person, no? Yeah, we will start with the Augustine's lecture, and hopefully he will be joining us soon.
Thank you very much, Chairman. I would like to present my paper on covariance matrix estimation based on matrix projection. And first, I would like to present the statistical background of my talk. Namely, we will consider an experiment in which on n experimental units, m characteristics are observed on each experimental unit. And I will assume that each vector of observation in each experimental unit has the same distribution with expectation vector mu and covariance matrix sigma. Moreover, I will assume that observations are independent. So the observation can be written down on the form of matrix X, in which each row corresponds to observation vector, and the rows of this random observation matrix X are independent, and rows has the same distribution. And I will assume that that observation matrix X is normally distributed. So my problem is to estimate unknown covariance matrix sigma, but I will have additional information about structure of this covariance matrix sigma. Namely, I will assume that sigma is linearly structured. It means that matrix sigma can be presented as a linear combination of known matrices VI. And I will denote this structure by S, written S. And matrices, it can be emphasized that matrices VI are not necessarily definite, positive definite, but I will assume that matrix sigma is positive definite. So I would like to present some such covariance structures. First, it is compound symmetry structure. It consists of matrices that with the same diagonal elements and the same off-diagonal elements. And such structure will be denoted by S sub CS. The next structure, it is banded structure of banded Teplitz matrices, and it consists of matrices with the same diagonal elements and the same elements on particular subdiagonals and superdiagonals I. And other elements are equal to 0. So the matrix H, it is the matrix HI, it is the matrix with ones on I's super and subdiagonals, and with other elements equal to 0. And such structure I will denote by S sub TP, when P is describing the band in this structure. And the last structure I would like to present, it is the block structured matrices. It corresponds to the experiment in which we are interested in studying cross-covariance of two subvectors of observation. Namely, it corresponds to the case when our characteristic can be divided into two groups, and its observation on characteristic from these two groups are what is interesting in such experiment. It is to study its so-called cross-covariance matrix. It means the off-diagonal matrix of block-divided matrix sigma. And general assumption about the structure is the following: that block diagonal elements sigma 1, sigma 2 are arbitrary symmetric matrices, and off-diagonal elements, for example, in this case, has this off-diagonal blocks have the same elements equal to gamma. And we can also consider, for example, combination of such structure, for example, compound symmetry structure and Teplitz-banded matrices. And as I told, our problem here is to estimate a unknown covariance matrix sigma. But what we required from estimator is that it should be structured, having the same structure as unknown matrix sigma, and moreover, that it is positive definite and usually also well conditioned. And that common method of deriving such estimator is maximum likelihood estimation method. It consists of maximization of likelihood function of the following form, where S, it is usual sample covariance matrix, and this maximization should be done with restriction on the matrix sigma, that is a structured matrix, and positive definite. And especially because of this constraint, the solution of this maximization problem is in general numerically complex, and it is necessary to use some iteration procedure that is time-consuming in general, but not always. In the case of some special structure, we can get the maximum likelihood estimator very easy. We can get it as a function of sample covariance matrix. It means maximum likelihood estimator in unstructured case. And it is the case of so-called quadratic space. It means that when we consider it structure is quadratic space, it is linear space and quadratic space. What does it mean? Quadratic space, it means that when the matrix belongs to the structure S, its square also belongs to the matrix S. And in the paper by Philippe et al., 2020, we will study this problem of obtaining a maximum likelihood estimator of sigma when sigma is linearly structured, but the structure is also quadratic space. And this estimator is nothing more than usual projection of sample covariance matrix onto the structure S. Or equivalently, we can present this estimator as minimum over the structured sigma of Frobenius loss function. To get this project, as I told, the projection is relatively easy. It is enough to derive a orthonormal basis of the quadratic space, but such a basis that is consists of non-negative definite matrices. It is the case when the quadratic space is commutative. And the example of such quadratic space is the structure of compound symmetry matrices. And this special basis consists of two matrices: this projection on the linear subspace, vector linear subspace generated by vector of ones, and the end of projector to its orthocomplement. And after normalizing, we can get such orthonormal basis. Of course, we can get this projection using also other orthonormal basis. So it is a question whether we can use the same projection procedure in the case when our structure is not quadratic space, and it is unfortunately quite common. And such a method of projection estimator, it means when the estimator is simply projection of sample covariance matrix of the structure S, was studied by Olson and von Rosen in the paper 2010. And such estimator has very good properties. First, it is explicit estimator, so we can study its property, and it is unbiased, it is a consistent estimator. So, unfortunately, it has some drawbacks, and it follows, for example, from paper by Fuller and Jensen from 2013. Namely, when the structure is not quadratic, so projection of sample covariance matrix is not, in general, it is not preserving, this projection is not preserving its definiteness. It means that a resulting estimator in some cases can be, for example, indefinite or can be singular. So it is not good property of estimator. And I would like to present example of such projection, namely the matrix on the left-hand side. It is compound symmetry matrix that is positive definite, but its projection on the right-hand side, a projection of the structure of banded Teplitz matrices T1, it's one band, is a non-definite matrix. So, as I thought, it is not fulfilling our requirements, such estimator, to be a positive definite. It is only structured. So now I would like to present some way to get structured estimators and positive definite or definite general. So the first such method can be based on projection of the sample covariance matrix, not on the structure, but on the convex cone of non-negative definite structured matrices. Such procedure is presented in the paper Philippe et al. In 2018, and we were also presenting this procedure of projection of on the convex cone of non-negative definite structured matrices. It was the case of Teplitz banded matrices. So why not to use this projection as estimator? But such estimator has also some drawbacks. One, it is the following: that such estimator is definite, but it can be only non-negative definite. It means it can be singular or semi-positive definite. It means it can be singular. And moreover, the procedure of such projection is numerically complex and time-consuming. So the next proposal to improve such projection, to propose estimator based on projection, but improved projection of sample covariance matrix on the structure S, I will denote it's by S sub P, is proposed by John and Mieljos in the paper 2020. They were proposing shrinkage method to get estimator of sigma, denoted here by sigma hat. Such estimator is convex combination of two matrices, so-called target matrix T, that is structured and positive definite, and projection matrix SP. And the problem here is with selection of target matrix T, and the second problem is with getting optimal lambda. So this what was shown in the paper, that the property of estimators strongly depend on the choice of matrix T. And they were studying they were proposing some choice of matrix T, and once the target matrix T was proposed, it can be given matrix or matrix multiplied by, or its multiplication, it can be multiplied by some coefficient, or it can be linear combination of some matrices, structured matrices. But such combinations that resulting matrix T is positive definite. So it is a problem of evaluating the coefficient of such shrinkage estimator. It can be done by optimization of this coefficient through, for example, some risk function. Some standard method is based on Frobenius risk function. Such optimal coefficient are a function of unknown matrix, covariance matrix sigma. So this covariance can be replaced by sample covariance matrix S, And such way we are getting so-called empirical coefficient. And it was the way proposed by John and Mieljot, and they were studying the property. And the property of these methods were quite satisfactory. But as I told you, it was still the problem of the choice of matrix T and lambda. So what I would like to propose, it is special method of the choice of T, and the resulting estimator has a bit different form. So I will use a bit different name. And as a starting point of target matrix T, this matrix T, what I would like to propose, it's a positive combination of the basis of a quadratic subspace of our considered structure S. And the selection procedure of such estimator, proposed estimator, is the following. The projection, first we project the sum covariance matrix S on the structure S, and if this projection matrix SP is positive definite, then we are using this projection as estimator of unknown sigma hat. So this estimator will be denoted by sigma hat. So it is exactly the same estimator as estimator proposed in paper by Olson and von Rosen. So when this estimator is when this estimator is not positive definite, so I propose the estimator that is sum of two matrices S1 and matrix S2 multiplied by some coefficient lambda. What is matrix S1? S1 is projection of some covariance matrix on a quadratic subspace of matrix S. And the projection of some covariance matrix on the orthocomplement of this quadratic subspace, orthocomplement S, it will be denoted by S2. And lambda, it is coefficient from the interval from 0 to 1. So such form of estimators was obtained in some cases directly by using the target matrix as linear combination of the basis of this quadratic subspace. And I would like to present here some example of such quadratic subspace. So the first, it is the case of structured Teplitz matrices. The quadratic subspace, the biggest quadratic subspace, the only quadratic subspace, it is a subspace generated by identity matrix. And it is quite common assumption that the identity matrix belongs to structure. So what we know that in such case, such quadratic subspace exists. And the projection on this quadratic subspace, the projection S1, is a very simple form. It is the identity matrix multiplied by average elements, diagonal elements of sample covariance matrix S. And the second case, it is the combination of a compound symmetry structure and Teplitz, for example, T1 structure or other. So the quadratic subspace in such case, it is a subspace of compound symmetry matrix. And the projection of matrix S on this subspace has the following form. It is the matrix with the same diagonal elements equal to the average diagonal elements of sample covariance matrix S, and its off-diagonal elements are also equal, and they are equal to the average of off-diagonal matrix of sample covariance matrix S. And so we see that in both cases, we can use as target, the first case, we can use as target matrix the identity matrix or matrix proportional to identity matrix. And in the second case, we can use, and it is quite important here, for example, we can propose as target matrix a positive combination of basis matrices of compound symmetry matrix, but such we propose to use such a basis that consists of non-negative definite matrices. And when this quadratic subspace is commuting, it is always the case that such bases exist. And it's usually such basis matrices are proportional to idempotent symmetric matrices. So the projection S1 is easy to obtain. S2, it is nothing more than a projection that SP minus S1. So it's also numerically very simple. And the problem now it is in evaluating the lambda, the coefficient lambda. It also follows from optimization procedure. And the lambda is a function of unknown covariance matrix sigma. And once replacing this unknown covariance matrix sigma by sample covariance matrix S, we are getting so-called empirical lambda. So a resulting estimator consists of two projections and with some empirical coefficient lambda. And what is interesting is that this estimator has, because of this formula, it can be studied by using some simulation study. And I would like to present the result of such simulation study. So the first, it is the purpose of this simulation study was to compare this so-called quasi-shrinkage estimator, sigma hat, with maximum likelihood estimator. And the statistical property of both estimators are similar. In most cases, maximum likelihood estimator has a bit better statistical properties, such as risk function, smaller value of risk function, or unbiasedness and its dispersion and so on. But in some cases, it was not so uniform advantage. The MLE estimator was not uniformly better. And what is a big advantage of this quasi-shrinkage estimator? It is this simple procedure of getting this estimator and computing the estimator, this quasi-shrinkage estimator, sigma hat, it can be more than, for example, 500 times faster than computing maximum likelihood estimate. But of course, it depends on the structure, on the number of characteristic M and so on, or number of sample size M. But in general, it can be recommended as very fast estimator and having quite good statistical properties in comparison with MLE. What is also quite important conclusion from our simulation study that with growing N, both estimators are let's say closer, and its statistical properties are more similar. So I would like to recommend such estimator, especially in the case when the fast procedure is required. For example, the problem of machine learning and so on. And what is also important that because sample covariance matrix is random, so it is not necessary to use the very how to say, exact procedure. So at the end, I would like to express my thanks to my collaborators, Malwina Janiszewska, Adam Jeldzic, and Monika Okrzycka. And now I would like to present the list of references. And as you can see, most of these papers are relatively recent. And especially I would like to focus on the last one paper, because in the abstract I was mentioned about entropy loss function. So in this paper we're studying the use of entropy loss function in the structure selection problem. And in the selection procedure, the procedure of approximation of some covariance matrix using the entropy loss function was studied, and this approximation of some covariance matrix by structured matrices using entropy loss function can be also treated as an estimator of unknown covariance matrix, but unfortunately it is also quite numerically not efficient. And the last two paper on my reference list are following, and the last paper is the paper in which this projection estimator was studied in the setup of growth curve model. So I would like to thank for your attention. Thank you very much.
So welcome to my presentation on residual analysis for the Manova model.
Sorry, I thought I heard Martin. So, nice to see you, Augustin.
Yeah, hello. I have problem with connection, but finally I will solve this problem.
Yeah,
I was solving it.
And floor is open for discussion here. Is there anyone who have comments or to this interesting work? Right, do you hear me?
Yes, yes.
You hear me, but they're on the other side of the globe.
Yes, there are people hearing you from Portugal. Hello, how are you, Professor?
Yeah,
well,
nice to hear you.
Yes. It is a very interesting presentation, and it's nice to see Professor Markiewicz presenting a nice work. And I'd like to make some claps for his research group, who made a method that is 500 times faster than MLA. It's a good notice, and it's very, very interesting presentation. It's just my remark. Congratulations.
Thank you very much.
More comments?
Anyway, I like to put up my, not remarks, in fact, I must convey him the thanks. Just yesterday only he struggled hard and made this recording possible, and he sent it to us. And today also with all trouble he came. Thank you, Augustine.
Thank you very much. You're welcome.
Okay. And I don't see any more hands up or some more willing to say something. So then I think we move to the last speaker of this session. And this is Professor Martin Singel. So welcome. Hey. So we have another Swedish friend here.
How are you?
I'm fine. I'm very fine. I'm very sorry I cannot
see you.
Yeah, I'm very sorry I cannot be in Manipal now. It would be wonderful. Here is very gray and very boring weather right now. So
it is quite warm here. Not hot.
So, sounds good. Okay.
Okay, please go on.
Raksha, please.
So welcome to my presentation on residual analysis for the Manova Model. First of all, I would like to thank the organizer for letting me present this talk here today. And I'm very sorry that I cannot be in Manipal in India. I was there for 3 years ago, and it was a real pleasure and a very good conference. So I'm really sorry to not be able to attend the conference this year as well. Hopefully next time. This talk is a joint work together with our PhD student, Beatrice Bukasenge, and Professor Dietrich von Rosen. And the talk is based on 4 papers. So the content of the presentation is, first we will have a multivariate linear model. We'll talk about the Manova model. Then I will talk about hypothesis testing for the Manova model. And then we'll come into the G-Manova model, which is also known as the growth curve model, and the mixture of those 2 models known as the G-Manova-Manova model. And then we'll talk about estimation, fitted values, and where the focus will be on the residuals and the interpretation of the residuals, and then some properties of the residuals. And we will see that the distribution is for some of the residuals is too easy to find. So in that case, we'll use what is known as the parametric bootstrap. So let us first start with the multivariate linear model. So assume that we have some kind of observation matrix or data matrix, which is a P by N matrix, X here. And then we would like to model the mean, the expectation for X, as a matrix called B times C. B is the unknown parameter matrix, and C is the known design matrix. And then plus some error, and I will assume that the error is matrix normal distributed. So sigma here means that we have the covariance matrix between the rows as sigma, and the covariance between the columns as identity, which means that we have independent observations. So we have the parameter matrix B, which is the one that we would like to estimate, and we have the parameter matrix sigma for the covariances that also need to be estimated. Since we have normal distribution here, we can just put up the MLEs, and we see that the MLEs for B hat is just X and then times C transpose C, C transpose inverse. And here I assume that C transpose has full rank. So the inverse exists. Otherwise, we can just use the generalized inverse instead. And then we have the estimator for the covariance matrix, and we know that the estimator for the covariance matrix, we can write it as the sum of squares for the residuals. So here we have R transpose, and R is just the residual matrix. So here it's just that we have X minus the estimated mean, and the estimated mean will just be, if we multiply here with the C here, we'll have BC, and then we'll see that we will have X times PC transpose here. So we will have this, and this is the projection matrix of the column space of C transpose. So you see that the covariance matrix is just estimated through the sum of squares of the residuals. And I will call this sum of squares of the residuals, I will call this S. Since X follows a normal distribution based on the E error matrix here, the residuals follows a normal distribution, because the residuals is just a linear transformation of the X matrix. So then it must be a normal distribution with mean 0, some covariance sigma, and then a covariance between the columns, which will be I minus the PC transpose. And this is just an orthogonal projection. So since we have a projection matrix here, we can see that this normal distribution here is singular. So if you look in this in more detail, how it looked like is that, okay, we have the estimator or the fitted mean will just be B hat C, and this is just X times PC transpose. So this is just a projection of the data on the column space of C transpose. And then we have the R hat, which is our residuals. And this can just be written as we do the projection on the orthogonal column space of C transpose. So if you look at the more schematic picture here, we can see that we have the full space. We decompose the full space into 2 parts. One is the column space of C transpose, and one is the column space of C transpose orthogonal. And then we see on the column space of C transpose, we find the fitted value, and on the orthogonal part, we find the residual. And say that we would like to test a bilinear hypothesis for the Manova model. So say that we would like to test if FBG is equal to 0. And F and G are known matrices. So here is, for example, we can test if different parameters are equal, or if they are equal and equal to 0, and so on. But if we take this hypothesis, FBG is equal to 0, and we solve this for B, we will have this, and B is equal to F transpose O, and then theta 1 G transpose, and then theta 2 times GO prime. So this GO here is just a matrix that spans the orthogonal column space to G. But then we take this solution and we plug that one into the model. So if we plug that one into the model, then we will have that X is equal to, and then we have BC. So we take BC, so we just multiply with the C here and the C here, and then we will have this model instead. And as you can see here, we will have one part of this model which will be a Manova part. So here we see we have a Manova model, but here we have something that we will call the generalized Manova model. So this is the G Manova part. And this is also known as the growth curve model, this part here. And one can see that this is a special case of a model called the extended growth curve. And it's a special case because we have this, with the extended growth curve model, we have ABC and then some more ABC and so on. But here we see that the A here could be the identity matrix in this model here. So this is a special case of the extended growth curve model, which is known as the G Manova model. And so what is the interesting thing here is that you can see if you would like to test this hypothesis here, you can do that by considering the residual for this model here, for this G Manova model. And this is very interesting because then you can see if you reject the hypothesis up here, you can see why do you reject the hypothesis. You can see if it's due to some observation or is it due to the model assumption and what it will be. We would like to study the residuals for this G Manova model. So let us take an example where this model, the G Manova model can occur. So let us have an example with repeated measurements, and this is an example that would follow us through all the presentation here today. So we study a realistic but an artificial data. So we look at some data, and we made it artificial. So this is not a real data set, but it's very similar to some real studies that have happened. And here we have repeated measurements on 69 patients suffering from some disease. So we say that N is equal to 69. This is the individual suffering from the disease. And then we divide those two, all those 69 observations, we divide it into two groups. So we have 35 were randomized to treatment 1, and we call this group 1, and 34 were randomized to treatment 2, and we call them group 2. And then we're measuring something called the estimated autoimmunity, and this is our response. And we do this at some baseline, which is time 0, and this is the initiation of the treatment. And then we do it after 6, 12, and 18 months. So we do this as a repeated measurements. We have 4 observations on each individual. When we have this estimated autoimmunity, that a low value is good for the treatment. So we would like to see small values of the response. So this is the data. So we have a data matrix, which is our X. So the first 35 columns is group 1, and the next 34 columns is group 2. So we can look at the data here. So here you can see the blue ones are group 1, and the red ones are group 2. So here is just 69 different lines, 69 different profiles, and there is repeated measurements at 0. Time 0, 6, 12, and 18. And we will start to analyze this using a G Manova model, which is also known as the growth curve model. And the growth curve model is defined, first was defined, it was Rao did it in the 50s, but it was done more properly by Pothoff and Roy from 1964. So when you put up the growth curve model, you will have one part which is the Manova part, and this is this part here. We will have the BC. So B is the unknown parameter, and C is the design matrix that we will use to separate groups. So this is what is called the between individual design matrix, this C here. And then we'll have another design matrix A here, which is the within design matrix. And this is just used to model the repeated measurements. So the mean structure here will be an ABC. And then we have an error matrix, which is E. So here we say that E is a P times N, and it's a zero mean, and the covariance matrix, this is covariance between the rows, will be sigma, and covariance between the columns will be identity. It means that all the individuals in our study are independent. So let us see how we can use this for our model that we have here with the repeated measurements on this disease. So say that we would like to model linear growth. So if we would like to model linear growth, we start with some beta 1. So this is the intercept. And then we have a slope parameter here, which is beta 2, B2. And then we say that this is after 6 months, after 12 months, and after 18 months. So this is the linear growth that we have for group 1 and for group 2. So we have 2 different intercepts and 2 different slopes for the 2 different groups. And this can be done just using the parameter matrix B, which is B11, B12, B21, B22. So this is the intercepts that we have for the 2 groups here. And this is the slopes that we have for the 2 groups here. And then we have the within design matrix A. So this is the one here is for the intercepts. And this one is for the slopes. And then we have our C matrix, which is the between design matrix to separate 2 different groups. So then we have, this is the one vector, 35 ones, and this is transpose. So this means a row with 35 ones, and then we have 34 zeros after that. So this is just to pick group 1, and this is to pick group 2. We can find the MLE for our growth curve. And the MLE for the growth curve doesn't look so much straightforward in the beginning as we did for the Manova, but if we look at it more carefully, you will see that this is also projection on different spaces. So first we can estimate the parameter matrix, and we do that by taking this matrix here, what we have here, as you see, and then we have the Manova part, which is this part here. So when we have the repeated measurements, we will also have this matrix here. If we take the growth curve model and put in identity as A, then it means that we just have the Manova model. And if we do that, you will see that this one here will cancel, because here will be A is identity, then it means S here and S inverse here. So we'll have identity and only have the estimator for the Manova model. If we multiply this one here with an A and a C here, so we have the fitted values, this means A, B hat C, then we can see that we have projection matrices here. So we have the projection matrix that we have before for the Manova model, but then we also have some projection matrix here. So this is a projection matrix on the column space of A, but with an inner product defined by S. And here is a bit, if you compare to the Manova model, we have a bit more problem here with the growth curve model, because here the S is also involved here when we do the estimation of the mean. When we did the estimation of the mean for the Manova model, we only have this part here. And then when we estimate the covariance matrix, we can just do that by taking the sum of squares for the residuals. And so here we see that we have X minus the fitted value, and then we take the same transpose. And this here, in this model, it can be divided into 2 parts. So we have what we had before, this S matrix, which is just the sum of squares of the residuals R, but there is also some other residuals, R1 here. So we have R1, R1 transpose. So we see that R1 is this part here, and R is this one as before. So if we look again at this picture here, we can see that we can take the full space, we can decompose this full space into a number of different parts. So we can look at the projections on the column space of C transpose and the column space of A. And as we saw, when we looked at the estimated fitted value, could be found by just taking the projection on the column space of A with an inner product S and the column space of C transpose. So then this part here. If we look at when we find the covariance matrix and with the estimator of the covariance matrix, this was just the sum of squares with the 2 different residuals here. So then you can see that we have this R as before, which is just a projection of the orthogonal space on the column space of C transpose, which is this one here. And then we also have this part here, R1, and this R1 here is just a projection of the orthogonal space to the column space of A and to the column space of C transpose. So then it's up here. So now we can see that we have this structure here now that we have, if we would like to find the residuals, we are on those two spaces here, and this is the space for the fitted. So let us now plug this one in, the data that we have in our example in the MLEs. So then we can find the MLEs for the P as this one here. So we have the intercepts and we have the slope parameters, and then you have the estimators for the covariance matrix like this. So if we do this, and if we plot these two models, those two linear models here, you can see there is a linear model for group 1 and a linear model for group 2. Here there seems to be this more or less the same intercept, but then they have different slopes. So it seems like the red group here seems to be treated better, because it seems that they get lower response with time. In this example that we have, say also that we recorded the age of the individuals in the entry of the study. And we also have an indicator whether or not the patient had previously treated for the disease. So we say that it was 0 if there was no treatment and 1 if there had. So how can we include those two covariates into the model? If we want to do that, then we must study Manova model. So in the Manova model, we have this Manova part, or the growth curve part, but then in this B2C2, here we can include the information we have from the covariates. So here we can include the age, for example, or we can include if the individuals were treated or not for this disease before. And this is known as the Manova model, and this is a special case of the extended growth curve model. In the extended growth curve model, you have a restriction on column spaces of C1 and C2 often. And this is just due to technical reasons that you would like to have unique estimators. But one can also see that you can put this restriction on the column spaces of A. So if you have the extended growth curve model, you have A1 here and you have A2 here. And then you should have that the column space of A1, which is this one here, should be included in the column space of A2. But in this case, you can see since A2 here is the identity matrix, you can see that this is always true, because the column space of A is always in the column space of the identity matrix. So here we will have no problem with the unique estimators when we find our MLEs. So if we use this for our data, and say, for example, that we would like to use the age as a covariate, then we can have our Manova model. We have within the design matrix for the repeated measurements. We have the between design matrix for the two different treatment groups. And then we have, for example, this C2 here. Here we can have that we assume that we have different effects for the two groups depending on age. So it can be like this. So then our C2 will be like this, and our beta 2 will be a 4 times 2 matrix. So soon here I will fit this model here with the data, so you will see how it looks like. But it can also be that we can assume that we have the same effect for the groups using just a C matrix like this. So here we have the same effect, and then we'll just have a B2 which will be 4 times 1, because then there will be different effects for the different repeated measurements of the 0, 6, 12, and 18 months, but we will have the same effect for the both groups. We can also have that they have been previously treated, and then we can have a model like this. So we can have a C2 like this. So here we have that the 13 or 22 patients, 22 individuals in the first group were previously treated. And then we have 24 individuals in the second group were previously treated. And we can also model that they have different effects for the different groups. So either we can model it like this, or we can model it like this. And this is just to put up different effects if the individuals have been previously treated or not for the disease. So here you see we have a matrix which is 4 times 1, because there we have the same effect for the two groups. Here we have a matrix which is 4 times 2, and here we have different effects for the two groups. And in a paper is that we discuss those different models and the consequences along with them, because some of those models will have quite interesting residuals, and we can see that some of the models are not good. For example, this model is not a good way to model it. This is much better, but there is drawbacks also with this. So then you can find the MLEs for the Manova model. And if you look at the MLEs, you can just put them up. And I will not go into the details here because you can find them in our first paper where we have found all the MLEs. And MLEs is, I mean, this is just a special case of the extended growth model. So the MLEs can also be found for this extended growth model, and then this is just a special case. So this can be used. And then we have the MLEs. So then we can just plug in the data. So then here I assume that we have H as a covariate, and we have different effects for the two different groups, the treatment groups that we have. So then we have this B1 and we have this B2, and then we have this covariance matrix. So here, if we plot this mean model here now, and here I have plotted them because now we also we must put in an H when we would like to plot. So I took the mean H for group 1 and the mean H for group 2, just to have some H to plot for. So here is the mean H for group 1 is 51.1 and the mean H for group 2 is 49.4. And then I put this into the model. So then I use this for the repeater measurements, for the linear growth, and then I use this for the covariance. So this is the effect for group 1, and this is the effect for group 2, the H effect. So if we do that, you will see that we have those two models here, and you can see there is a big difference in the beginning, but then they seem to be parallel after that. Since we put in this covariate, they will not be linear anymore, because then we'll have this H effect as well. So the fitted values is just the estimated mean model. So we plug in our estimates in here, in A1, B1, C1, and B2, C2. And then we have the fitted models. And it can be written in this way with the help of the projections. And the residuals we know is the observed value minus the fitted values. And they can be used for model validations. And it can also be used to find outliers and influential observations. And also, as we have seen, in the beginning when I talked about the Manova model, about the test statistics for different hypotheses. In this case, when we have this Manova model, the residuals can be written in this way. We have x minus x hat, and then we just plug in our fitted values, and we come up with where we have skipped a lot of details here. We come up with this expression for the residuals, and we can see that we have two parts. We have one part here, and we have one part here. So here I just summarize it with a theorem that the residuals for the Manova model can be written as R is equal to R1 plus R2. The R1 is the first part and R2 is the second part. And then R1 can also be divided into two parts, where we have here as the projection on the column space of A and the orthogonal projection of the column space of A. So here you see R1 is just projection on the column space of, or the orthogonal space of the column space of C2 and C1 prime. So this is what we had here, right? This is the orthogonal projection on the column space to this matrix here. And then we have this, that we divide this R1 into this, what is a projection on this space and a projection on this space. And then we have R2, which is a projection on this space and here on this space, on the orthogonal column space of A. And then it's just a question, how can we interpret those residuals? R1 and R2 has a clear meaning. And the first residual is the difference between the observations and the estimated mean, where we have not taken into account the model, the mean model. So here is just the sample means you can see, or similar at the means for the sample means for each group or each individual. So R1 can be used to detect outliers which deviate from others without taking into account the model assumption. We can also split R1 into those two different ways as we did before. So we have R11 and R22. And this is just if we want to take this into account with the within individuals and without this within individual model assumption. We can see that R2 is the observed mean, or the sample mean, minus the estimated mean model, I mean the fitted values. So I can rewrite R2 to just be this one here, that we have this observed mean minus the fitted values. So here we can really take into account the model assumptions. So R2 gives us information about the appropriateness of the model assumption about the mean structure. So let us again look at this first example with the data that we had. And here we had this data with 4 repeated measurements and 69 individuals. So we have 35 individuals from the first group and 34 individuals from the second group. So here we can see the residuals for R1, and here is the residuals for R2. And here we see nothing special. So the question is, what happens if we disturb any of the observations? So we can see that it looks quite nice. We can see in R2 that the largest values are 173, 129, and 114. So if I go back to this one, 173 is this one. 129 and 114, I guess, is this one and this one here. So what we would like to do now is we would like to disturb one patient at one time point. We will disturb one patient at all time points, and we will change the linear growth assumption to a quadratic group. And then later on, we will also do some parametric bootstrap to find out if some of the residuals are large enough to say that this model assumption that we have is not good, that we need to do something with the mean model. And this is, we will do parametric bootstrap for the second residuals R2. So let us first disturb this first patient. This is patient number 1 in group 1. So it should be like this, but we disturb this one here, so we put this one value instead, and we'll see if we can find this disturbance in the residuals. So if I just do this one and then I find out the residuals again, you can see that this one will come down here. So this blue one used to be here, but now I disturb this one, and this is at time point 2, and then we will see that this one is disturbed down here. If I also disturb all of the observations for patient 1, so instead of taking just this, which is the true observations, I disturb it, so I just lower it with 50%. I take 50% of the observations. So here we can see that if there is an outlier in one observation, then only one of the repeated measurements, as we can see, is disturbed in the residuals. But if there is a disturbance for observations for one individual in one group, then we see that for all the residuals here for that individual. Next, we would like to see what happens if we assume, instead of linear growth, we assume quadratic growth. So then I have disturbed this one, so the blue one, instead of being linear, we see that we have some quadratic trend here instead. So how can we see that for the residual R2? So if we look at the residual R2, we can see that the residual R1 is not changed. It's not affected at all, because here now I have disturbed all individuals in a group to be quadratic instead of being linear. But we can see in R2 that there is much more variation in the residual R2. So if you compare to this, here you see there all of them are more or less between -1 and 1. And they are the same for the first group and the second group. But if we look after we have disturbed the first group, there is more variation now in the first group than in the second group. If you look at the distribution for the residuals, for R1, one can easily see that R1 is matrix normal distributed because it's just a linear transformation of a normal distribution. Let us look at some properties of the residuals. So we can see that the expectation of R1 and R2, both of them are 0. We can see that the dispersion, we can find that the dispersion for R1 and dispersion of R2. That means that we can find the covariance matrices. We can also find the covariances between R1 and R2, R1 and X hat, and R1 and B, the estimators of B hat. And we can see that all of them are covariances are equal to 0. We have used parametric bootstrap to find out the distribution for the 3 largest values of R2. So what we do is that we fit the model, we find out the estimates, beta, B1, B2, and sigma. We plug this one into the model, then we simulate a number of observations from this model. And we do that m times. And for each time, we also find out the residuals. So that means that we have a setup with m residuals from this model. Now we have that, we find out the three large, I take k largest here, but the three largest by absolute value from R2. So we do that in each step here, each time we do the simulation. So that means that we have the R2, we take the largest value, and then we do that m times. And our m will be 10,000. Well, if you look at the original data, we have this R2 like this. So in the original data, we have 173, 129, and 114 for the three largest. And then it's just a question if this 173 is large enough to reject the hypothesis about linear growth, so that there should be some other mean structure. So I do parametric bootstrap with 10,000 times. I simulate, every time I simulate new data, I find out the residuals R2, and I keep track of the three largest. And I do that all the time. And here, for example, is the largest value, the largest residual in R2. And then I just take the cutoff point here for 95% and 99%. So we see 95% is 1.84, so it's here somewhere. So we have 95% of the data, 5% of the data here in the tape. And if we have 2.3 here, it's something here, we have 1% of the data here. On 5% test, it should be larger than 1.85, and on 1% test, we should be larger than 2.29. We have this one was 1.73. And here I also plotted out the cutoff points. So here is 1.85 and 2.3. And we see none of the observations is outside. None of the observations are in the tail from our parametric bootstrap. This means that we would not reject the mean model as linear growth. So what happens if we disturb the model? Can we find out that we have some other model? So we disturb it again with a quadratic growth. So here I put down quadratic growth for group 1, and we still have the linear growth for group 2. So then I find out the residuals from this model. So the residuals from this model were like this. So here we see that we have larger values, and mostly we have larger values here. So then is the question, are those now when we have a larger variation in our residuals, are those large enough to reject that this should be linear growth here, that we have linear growth for group 2, but not linear growth for group 1? Can we find out? Can we find that? So if I do my parametric bootstrap, I will come up with this one, 10,000 times. This is my cutoff point for 1% test and for 5% test. So we are now, over here is 1%, and over here is 5%. Then we can see that if I look at 5% cutoff, then we have those red lines here, and then there is a number of observations which is outside this one, which are really in the tail. So then it means here I would conclude that I would reject the null hypothesis, which would be that we have linear growth. So there will be some other mean model for the group 1 than it should be for group 2, where we have the linear model. To conclude this talk, I would say that the residuals for the Growthkin model was found out by Dietrich from 95, and he showed that the residuals were symmetrically distributed around 0, and he had obtained some moments as well. Similar results can be found for the Manova model, and then the residuals for the Manova model, we divide them into two parts, R1 and R2. One can easily, R1 is used to find outliers for individual outliers, and that one is normally distributed. And for R2, where we find out for the model validation, I mean to see if the mean model is correct, we did a parametric bootstrap because the distribution for R2 is not available in a simple form. Hypothesis testing for the Manova model, and how maybe you can improve the likelihood ratio test by studying the residuals for the Manova model instead. And lastly, I would say that the take home from this presentation would be that it's not always straightforward to study and understand the residuals for a multivariate linear models. When you look at the residuals for a linear regression, multiple linear regression, for example, they're quite nice. You can see if there is a quadratic term missing or anything like that. But it's not so easy when you look at the multivariate linear models to understand all those different parts from the residuals that you have. So thank you very much for your attention.
So thank you very much. A big hand. So, welcome with comments and discussions, please.
I think everything was super clear.
That was a nice lecture.
No one?
Yeah, one thing I observed is all the 3 lectures today are very interesting and covers many basic things, and I'm sure that students will go through these lectures again and again and learn more.
Okay, thank you. Okay, maybe it's time then to close this session. And there are coffee breaks, for some are lunch breaks waiting, and
No, for us, it is going to be dinner after some time.
yeah.
Yeah,
Okay.
today we will close our session by this lecture, and see you all in the tomorrow morning.
Yep.
Tomorrow night.
For you, right.
Okay. Thank you very much.
Thank you.
Okay, thank you.
Thank you. Bye.
Bye.
Raksha, over to you.
Thanks a lot, ladies and gentlemen, for joining us today. So let us meet tomorrow sharply at 9:10 IST. Thank you all.